I'm Nick Wagman.
And I'm Cole Netzman.
And Ned Landy's behind the camera. We're Group 6, and this is our project number 2. So for part 1, we were using the Lennard-Jones intermolecular potential energy equations in order to find the intermolecular distances. So E total is going to be the total energy in the atom, and you're finding that with respect to R, which is the intermolecular distance between the atoms. So we have an equation for pure aluminum and then also for pure iron. So in order to find R, we know that at equilibrium, the force between the atoms is going to be 0. That means that the derivative of those equations is going to be 0. So what I did is I found the general form of the Lennard-Jones equations. I took the derivatives of those, and then I solved them in order to find R naught, which would just be where the distance is 0. So that's where I get that equation from. Using that equation, I'm able to plug in the numbers from before, A and B for aluminum, into that equation from the last slide, and then I get 0.2806 nanometers as the intermolecular distance at equilibrium. And then same thing for iron, just different numbers into that same equation, and we get 0.2816 nanometers at equilibrium. So here we have the graph showing the distances and the energy in the atoms at those distances. So here at the bottom of the graph is where the atom will be at equilibrium, and at that point the distance is going to be 0.2806 nanometers in aluminum. And then same thing for iron, showing the same thing, just in a different spot. The equilibrium point, the distance is 0.2816 nanometers.
I'm Cole Netzman, and I'll be talking about calculating the elastic and bulk modulus from these two equations that we were given. So, starting with aluminum, we were given the dislocation energy equation for aluminum. As Nick had said before, this is the total energy with respect to the interatomic distance. So, we first will take the first derivative of this. This will give us a force equation based off of the distance in nanometers. We can plot that force equation here on this graph. We see that as the distance increases, the force initially skyrockets. So it's taking a lot of force to separate these atoms. But after a certain distance, this force begins to drop off. That means that the electromagnetic pull of these atoms becomes weaker as that distance increases. Now, the elastic modulus here on this graph is actually the slope of this line, which obviously is changing at all these positions. So when it crosses 0 here, this is where the atom is at neutral rest. So when the force is 0. Here, the elastic modulus is the greatest. Now, at the top, at the peak, obviously the slope becomes 0 at some point, and then becomes negative. As the elastic modulus becomes negative, the material becomes more plastic-like. So as we saw in the tensile test, as the material was pulled apart, it appeared more plastic-like. This is the prime reason for that. So we can calculate that, that neutral distance by setting that force equation equal to 0 and solving for the interatomic distance. Here, as Nick said, it came to 0.2806 nanometers. Now, to find the actual elastic modulus at that point, we can take another derivative of that force equation. So it would be our second derivative from that initial energy equation. And that gives us this equation right here, solving for the elastic modulus with respect to this interatomic distance at that neutral position. So when we work all this through, we put our neutral R distance in, we come to we come to see that the elastic modulus is 0.3582 gigapascals. And now we can convert this into the bulk modulus. They're related by this equation here, with V being the Poisson ratio. So for aluminum, in this case, it is 0.33. This is a unitless dimension. So in order to find the bulk modulus, we take our elastic modulus and we divide it by this equation, and that gives us 0.3512 gigapascals. So now for the iron, same steps. We have our initial energy equation. We'll take the first derivative of it. This will give us our force equation. And then we can plot this here. It's much the same as the aluminum. Obviously it's different, but pretty much the same shape graph. We see that at where force is equal to 0, this is where the elastic modulus, the number that we all know, this is where that will be the slope of the line. And as we talked about, as the line comes down, the slope becomes negative. That's where the iron will become more plastic-like. So, same thing for the iron as we did the aluminum. We take the force equation, we set it equal to 0, and we find that the interatomic distance at that neutral position is 0.2825. So then we'll take the force equation, we'll take the derivative again, and we'll get this equation here, elastic modulus, with respect to that interatomic distance at that neutral position. So now, just as before, we take that initial R distance and we put it into that new equation for the elastic modulus, and that comes to 0.3586 gigapascals. And then for the bulk modulus again, we use the Poisson ratio, and for iron, this one came to 0.291, again, dimensionless. And once we took our elastic modulus and divided it by this, we get 0.2860 gigapascals.
So my name is Ned Landy, and I'll be talking about the vacancy concentration for our materials. So what is vacancy? So vacancy is pretty much just within the crystal structure of a material, an atom is missing. So this is a point defect, and this can have multiple effects on the behavior of a material. So blacksmiths look for these defects, and they manipulate it with heat in order to create more of these defects. And the more defects that there are in a material, the easier it is to hit with a hammer and shape it into any material or shape you kind of want. So then in order to calculate vacancy and then the vacancy density, so there's two formulas that you need to use. So this is the formula for vacancy density, and then this is the actual number of vacancy in the material. So within this, these two equations, we have Avogadro's number, which is a constant that we all know, and then we have the number of atomic sites is what we're looking for with this. So that's just the density for those sites. And then this is the density of the actual atom, and this is the density or the atomic weight of that molecule. So using these two formulas, you first find the vacancy concentration, and then that you can see plugs into the equation, and then that'll let you know the amount of vacancies per meter cubed within the material. So in order to show the steps, these are the steps for the aluminum. So we know that Avogadro's number is as this, and then we looked up the density and the atomic weight for the material for aluminum. And then once you plug in these values, we found that there's around 1.31 times 10 to the 28 atoms per meter cubed. And that's the density of sites that you may find an atomic a point defect in, which is the vacancy of that atom. And then using this value for n, we converted that over into this equation. So the QV is, you find the value online, and it's the standard energy needed for the formation of a hole. So in order to get a point defect, you need to have a certain amount of energy to create it. So this is the standard for aluminum, and then this is a constant, and this is the room temperature in Kelvin. Notice how that, since T is on the bottom of this equation, as temperature rises, then the final number of holes will go up. So once you plug in all the values, we found that around 3.32 times 10 to the 15 vacancies per meter cubed were found within aluminum at room temperature. And those number of vacancies will only go up as the temperature increases. And then now for iron, so the process is the same, but if you look over here, we found that 8.49 times 10 to the 28 atoms per meter cube could potentially have those point defects. And plugging that into our equation to find the number of vacancies per meter cube, we find that it's only around 1.625 vacancies per meter cube, which is an extraordinary low number compared to aluminum. And that just shows how much stronger that iron is at room temperature. But note how if you increase the temperature, yet again, those number of vacancies will increase, and that's how blacksmiths makes floors and stuff, by increasing the number of vacancies and taking away the strength that iron has in its material. And this further pursues what I was just talking about. At room temperature, the vacancy concentrations are pretty low, especially for iron, only 1.6 per meter cube. But this means the effects on yield strength are pretty negligible. But as T increases, you'll note that the vacancies will increase exponentially. And this will affect the yield strength by making it much lower, and then the material becomes a lot more easy to work with in a shop.